So we just have one more example for this part, and then we're going to practice this part, and then we're going to see how much we get through for the notes for the other part, okay? And then that will determine what the homework is for tonight. Okay, so it says we have a function g with derivatives of all orders. The Maclaurin series for g is this part right here. And we're evaluating it at 1/2. It's an alternating series whose terms decrease in absolute value to 0. So we're going to find the approximation using the first two non-zero terms of the series, blah, blah, blah. So they didn't tell us in the instructions to use the alternating series error bound, but they did tell us that it was alternating and decreasing. So they said alternate and decrease. And so because of that, we're going to use the alternating series error bound. Which we would have assumed because that's the topic for today, but we're going to learn another error bound later. So, okay, so what do I have to do? We want g to be evaluated at 1/2. What's g?
G is the series.
It's not the whole thing. Well, I guess g, no, you're right. G is the whole thing. But they didn't tell us to use the whole thing. What did they tell us to use? First two non-zero terms, and we're plugging in 1/2. Okay, so I'm going to say that we're using first two non-zero terms would be the third degree. Are we okay with that? So first term, second term, and then we'll say that we're evaluating this at 1/2. So that's 1/6. We've got 1/8 divided by 5. 1/40th. Can we get a common denominator? We can do 240. There's one smaller than that, I think, but on my notes I did 240 also. So yeah, so it would be 40 minus 6 over 240. The funny thing about my notes is I didn't simplify it either. I got the answer and I could simplify and I did not. So this is 34 over 240, and that's the answer I left on my notes. But we could simplify it. What would it be? Half of 34 is 17. I don't think it's going to reduce. So 17 over 120, I think, is about as simple as it's going to get. So that's the approximation. Yeah. So then for the error, what are we going to do for that? Yeah, it's the next term. Less than or equal to, and then what's the next term? Or absolute value of the next term, right? X to the 5th. So it would be 1/2 to the 5th over 7. And we want to show that that is less than 1/200th. So I'm going to go ahead and write that that approximation is less than 1/200th over there. Now on an FRQ, if you were like, I don't want to mess that up, and you are convinced that you did it right, you can go ahead and leave it on an FRQ. You do not have to simplify that. Okay? But this is not an FRQ, so we're just going to go ahead and make sure. So 1/2 to the 5th, what is that?
32.
32. So this is 1 over 32 times 7. 7 times 30. 7 times 3? Yeah, 210. 7 times 30 is 210. 7 times 2, so 210 plus 14. 224. And is that less than 1/200th? Yes, because the denominator is bigger, so the fraction is smaller. Good, so we proved it. Wasn't that fun? Yes, Miss Rice? Marvelous. All right, so for today and tomorrow, when we do the alternating series error bound or the next error bound we're going to learn, there's a lot of calculator active questions. And I was very deliberate to put calculators next to the ones that were calculator active. However, when we take the test, they will all be calculator inactive, which means you're going to have fractions, whatever. So on the assignments, we're going to have some decimal problems just so you can plug them in, get crazy answers, whatever. But when we actually do take it on the test, they will be nicer numbers. Like this would have been a very fair FRQ question on a test. This would have been kind of in line with what they end up doing, okay? So just a heads up on that. Yes, lots and lots of calculator active the next 2 days, but on the AP exam, this will definitely be calculator inactive. It is always FRQ 6. I have never seen it be another FRQ that's not FRQ 6 for like the last 20 years. So if they change it, that would be spectacular. Yeah, so this is most likely going to be a calculator inactive question.
If you do alternate series error bound thing correctly, will it always work out? Like,
Yeah, if they say show that it does this, then that's supposed to be true. It really does that,
okay, so
and you're
it's not
supposed
like
to get something.
You do this and then you have to do the error to say whether it's right or wrong.
No.
Silly. Okay.
No. So when I was on the other ones, when I was, is this what you're talking about? Saying that it's in between the two values?
I was just wondering because you said if you are confident that you did it right.
Yeah. If
then
you
can
know,
leave it.
yeah. So
if, like it'll always work out.
It'll always work out based on the problem. So the only reason that I would do this on an FRQ is because I'd want to make sure that my computations, that I'd like plug stuff in, right? Like if I wasn't sure about this, I'd take it all the way to the end just to make sure the fraction really was less. But if I know I did the problem right, I've practiced a bunch of these, I would probably leave it there because I'd want to get full credit and not make a computation mistake. Yeah.
With the, if you would go back to the previous page, will it most of the time be asking for the error bound, or will it? Are there instances in which it would ask for the integral?
It typically asks for the error bound, which is the actual number of how far off you can be. I have not typically seen them say find the interval. The reason I showed you how the interval works is so you kind of understood what error bound means, that it's an upper bound and a lower bound. They go both directions from your approximation. But that's typically not the answer they want. Typically, they just want to know the error bound, which is a fancy way of saying how far off could your answer be. It could be off by 1/6. It could be off by 1/224th. Each way, up or down. Yeah. Okay. Makes sense? Brains are okay? All right. So let me get this assignment out.